Some of my fondest childhood memories involved going bowling with my family. Now, it wasn't so much the activity that excited me, but rather that the bowling alley was decorated with UV lights, which would cause my white clothing to glow in the dark. I didn't know it at the time, but this was due to the presence of fluorescent molecules in textiles to make them appear brighter. In fact, fluorescent molecules are ubiquitous in our everyday lives. They're found in papers as brightening agents. They're used in road signs to improve visibility at greater distances. And in biomedical applications, they're used as probes for imaging or as biomarkers to track processes like drug delivery. It might surprise you to learn that lignin is also fluorescent. Here, the phenolic groups in its structure are able to absorb light and re-emit it at longer, less harmful wavelengths. Lignin also possesses many benefits when considering the development of lignin-based fluorescent technologies. It is highly abundant, it is non-toxic to many organisms, and when it's in its colloidal particle form, it forms stable dispersions in water. Yet, in order to develop these technologies, a more sophisticated fundamental understanding is required. How does lignin structure impact its fluorescent behavior? And how does this behavior change when lignin is in its particulate form? My work aims to answer these questions. I start by using technical lignins of different sources. From these lignins, I produce monodispersed particles ranging in their sizes and surface chemistries. I then study their fluorescent behavior, where I obtain a map that corresponds to the fluorescent emission intensity over a range of wavelengths. Using machine learning techniques, I study how these fluorescent maps connect to the lignin structure. And what I find is fascinating. Using the fluorescent data alone, I'm able to distinguish the initial lignins from one another. I also find that the fluorescent maps have trends that correspond to particle properties such as the particle size. Finally, I aim to connect this information with particle functionality, such as their antioxidant activity. Our group is aiming to consolidate this information into a lignin library containing characterization data of lignins from different sources and extraction procedures. I believe the addition of fluorescence data will allow for more rapid identification of structure, property, and performance relationships. Furthermore, I see benefits in using this information for the development of high-value UV protectant applications, such as cosmetics, where fluorescence and antioxidant activity can also play a role. As a kid in the bowling alley, I didn't realize how broad the applications of fluorescent molecules are. But now I'm glad to know that future fluorescent technologies can harness the power of trees. Thank you.